All right, in this video, I am going to show you how to use these known sums in actual problems. Okay, so we're going to look at calculating regular sums, and then we're going to do sums as n goes to infinity within a limit. All right, so we're going to look at a couple of those as well. So first, let's do the sum from I equals 1 to n of I squared plus 3i plus 4. Right? So what we can do here is we can kind of separate this out, right? So if this is the expression that we want to sum, I can split this up to sum of the first term plus sum of the second term plus sum of the last term. And then as I split this up, I am going to take this constant out front. So this is the sum of I equals 1 to n of I squared. Okay, and then I'm going to take the constant out front 3 times the sum from 1 equals n of I plus, go ahead and leave that sum, that constant in there, okay, the sum of 4. So when you split it up this way, we can use these known sums, right? Because what is the sum of I squared? We don't have to prove it. We can just plug it in. We're going to assume all of these are true. So the sum of I squared is n times n plus 1 times 2n plus 1 divided by 6. So I'm going to substitute that here. Plus, now I have 3 times the sum of I, right? We know what the sum of I is. We can assume that this is true. If we sum I n times, we're going to get n times n plus 1 divided by 2. Now we have this 3 out in front, so we're going to do 3 times that quantity, n times n plus 1 divided by 2, right? Plus, what's the sum of a constant, right? It's the constant times n if we're summing from 1 to n. And so we're just going to get 4n here, right? So what do we need to do? We probably need to get a common denominator, right? And factor as well as possible, all right? So I'm just going to write one fraction here. So I have a denominator of 2 here, a denominator of 6 here, and a denominator of 1. So I'm going to multiply this fraction by 3 over 3, and I'll multiply this fraction by 6 over 6. Right? So now that I have a common denominator, n times n plus 1 times 2n plus 1 over 6, this fraction is now 9n times n plus 1 over 6, and this last fraction is 24n divided by 6, right? Let's go ahead and just factor, okay, what we can. So every single fraction has over 6 now. So we can take out a 1/6, right? And in the numerators, every single numerator has a single n, right? So it looks like we can take out n over 6. So if I take out an n over 6, I'm left with n plus 1 times 2n plus 1 in the first term. I'm left with 9 times n plus 1 in the second term, and then I'm left with 24 here. All right, so you know what's next. Don't leave it here. All right, go ahead and multiply that out. So let me go ahead and FOIL this. 2n squared plus 3n plus 1. This is 9n plus 9. And this is just 24. So we're going to get n over 6 times 2n squared. 3n and 9n is 12n. 1, 9, and 24 is 34. Right? It looks like we can factor. This cannot be factorable. All right? So it looks like we could take a 2 out, right, out of each one of these. Now if I take a 2 out, that's going to go up top here, and that's going to reduce with the 6. So I'm going to take the 2 out. So I'm going to get n over 3 times n squared plus 6n plus 17. Right? Now this doesn't factor, so we've factored this completely. Right? So when you go to simplify, get a common denominator and then make sure it's factored as far as it can go. All right? So here we have a final answer. So just to recap, right? We started with this sum, I squared plus 3i plus 4. We split it up so that we can use our known sums, right? We have a sum for I squared, we have a sum for I, we have a sum for a constant, and we just plugged in those formulas. And then from there, it's just some algebraic simplification. All right? Let's try another. Let's do the summation I equals 1 to n I times I plus 1 times I plus 2. Right? Now remember, we can't split it up the first time, the summation of the first times the summation of the second times the summation of the third. It doesn't work for multiplication or division. And so what we're going to have to do here is we're going to have to actually multiply this together. All right. So let's go ahead. I'm going to multiply these two together first. So I plus 1 times I plus 2 is I squared plus 2i plus 1i is 3i plus 2. And then I'm going to multiply that, right, by the I here. And so I'm going to get the summation I equals 1 to n of I cubed plus 3i squared plus 2i. All right? So now what I want to do is I want to take the sum of each term, right? And I'm going to look for those known sums, all right? So I want to separate the 3 from the I squared, and I want to separate the 2 from the I because those are the formulas we have, right? We have the formula for I, we have the formula for I cubed, and we have the formula for I squared. So I'm going to separate this up, all right? So this is the summation from I equals 1 to n of I cubed plus 3 times the summation I equals 1 to n of I squared plus 2 times the summation I equals 1 to n of I. Right? So here, the summation of I cubed has a known formula that we can use. Right? We're going to get n times n plus 1 divided by 2 quantity squared. Right? The I squared has a known formula that we can use. So we're going to get 3 times n plus 1 times 2n plus 1 all over 6. Right? So the 3 and the 6 will reduce eventually. Plus 2. And then the summation of I has a known formula. Right? And the sum of I is n times n plus 1 all divided by 2. Right, so I'm gonna go and simplify this a little bit. I'm gonna go ahead and square these out. Okay, so I have n squared times n plus 1 squared over 4. Right, and then in the second one, the 3 and the 6 will cancel. So I have n times n plus 1 times 2n plus 1 over 2. And then the last one, the 2's are going to cancel, and I have n times n plus 1 only. Right? So I do want to get a common denominator and factor, just like last time. So the common denominator looks like it's going to be 4. So I'm going to multiply this one by 2 over 2, and I'm going to multiply the last one by 4 over 4. And so I'm going to get n squared times n plus 1 squared over 4 plus 2n times n plus 1 times 2n plus 1 over 4 plus 4n times n plus 1 over 4. Okay. So what can we factor out? Right? This time, This time every term has over 4, so we can take out the 1/4. Every term has an n, a single n. Every term actually has an n plus 1 as well, right? So I'm going to factor out n times n plus 1 over 4. So if I factor out n times n plus 1, the first term I'm left with n times n plus 1. The second term I'm left with 2 times 2n plus 1. And the last term I'm left with just 4. Okay. So let's go ahead and simplify inside the parentheses here. This is n squared and n. This is 4n plus 2 plus 4. So I'm going to get n times n plus 1 over 4 times n squared plus 5n plus 6. Does that factor? Yep. Okay, this what's left over cannot factor, right? It has to be factored completely. So n squared plus n, just double checking my work. N squared, 5n, and 6. Yeah, because this factors to n plus 2 times n plus 3, correct? So it looks like I should factor it. So I'm going to get n times n plus 1 times n plus 2 times n plus 3 all over 4, which is a very, very nice number. Okay, I really like that, right, as an answer. All right, so that's how you're going to work those I summations. You're just going to break up your polynomial to known I sums, fit them in, and then use your algebraic magical powers to simplify this to a nice, pretty, simple result. All right, guys. The piece de resistance is how to evaluate an n sum as n goes to infinity, right? Because right now n is a finite number, right? So we're going to look at the limit as n goes to infinity of a sum. Okay, 3 over n times I over n squared plus 1. All right, so you're going to tackle the sum first, okay, and then worry about the limit last. All right, so what I'd like to do is I'd like to go ahead and multiply this out. So I over n squared is just I squared over n squared. So I'm going to go ahead and distribute the 3 over n to both of these. All right. So I have the limit of the sum, and then my first term is 3i squared over n cubed, right? Because we have 3i squared on top. N squared times n is n cubed. And then if I distribute the 3 over n, I get 3 over n, right? So now I am summing these two terms, right? So when we're summing the I terms, anything that's not an I is deemed a constant, right? So applying the limit last, right? What I want to do is I want to do the sum of these two terms. So the I squared is what I'm summing. That's the index. 3 over n cubed is just a constant, right? Same thing with 3 over n. It's just a constant, right? So I'm going to factor everything that's not an I out in front of that sum. So I'm going to get the limit as n goes to infinity of, let me go ahead and put a bracket here maybe, 3 over n cubed times the sum of I squared, right, plus, I'm going to go ahead and take this constant out as well, 3 over n times the sum of 1, right? Because if we take 3 over n out, we're just left with 1 there. All right, so the sum of I squared has a known formula. The sum of 1 has a known formula, right? The sum of 1 is n. So what we're going to get here is the limit as n goes to infinity. The constant 3 over n cubed is going to be multiplied times the known form for I squared. So we're going to get n times n plus 1 times 2n plus 1 all over 6. Right? And then this constant 3 over n gets multiplied times the sum of 1, so it's 3 over n. The sum of 1 is n. Right? So what happens now is we're going to go ahead and reduce some of this, right? I'm going to go ahead and reduce the 3 over the 6. Okay, I'm going to cancel an n. And then I'm going to let the n's cancel here. So now I have the limit as n goes to infinity of n plus 1 times 2n plus 1 over n 2n squared plus 3, right? And I want to take the limit of this now, right? I'm not going to bother by getting a common denominator here, right? We just want to take the limit. So let me go ahead and multiply this out. The limit as n goes to infinity. If I distribute the top, I'm going to get 2n squared plus 3n plus 1 all over 2n squared. Okay, and then we're going to add a 3 to that. And we're taking the limit of all of this, right? So what happens here if we take as n goes to infinity of a fraction? Right? Remember, we divide by the highest power of x in the denominator, right? So let's go ahead and do that, okay? Well, think about it. If we divide everything by n squared, right, we're just going to be left with 2 over 2, 3 over n, and 1 over n squared, right? You remember doing that? But the other thing we can think about is this is, as n goes to infinity, it's basically the horizontal asymptote of this function, right? So if the powers match, then we're just going to get the leading coefficient over the leading coefficient, right? And so we should just get 1. So either way, we should just get 1. I'm going to go ahead and divide everything by n squared, right? So I'm going to get divide by n squared, divide by n squared, divide by n squared, divide by n squared. All right, here we go. So 2n squared over n squared is 2. This is 3 over n. And this is 1 over n squared. 2n squared over n squared is 2, right? So remember, everything left over n is going to go to 0. If n is going to infinity, this is going to go to 0. This is going to go to 0. So we end up with 2 over 2, which is 1. And then the limit of a constant is just a constant. And so we get a final answer of 4. Right? One more. Okay? One more. Now, of course, I'll be happy to work more of these with you. Okay, these Zoom meetings are going well. I have a whiteboard on there that I can just work problems on over and over. Those of you who have been attending, I think, are getting some help out of it. So more of you just need to start popping in. All right. So one more here on the video. All right. So let's look at the following. All right, here we go. The limit as n goes to infinity of the sum from I equals 1 to n of 2 over n times 2i over n cubed plus 5 times 2i over n. Right? So the first thing we need to do is we really need to multiply all this out. Okay, so I am going to go ahead and cube everything, distribute the 5 and distribute the 2 over n, just to kind of expand this form here. So I have the limit to be applied last. We're going to do the sum first. So 2i over n cubed is 8i cubed over n cubed. 8i cubed times 2 is 16i cubed. N cubed times n is n to the 4th. All right, we're going to get 10i over n here. 10i times 2 is 20i. N times n is n squared. Right? So if I multiply it all out, this is what I'm left with. Okay? So here's where we're going to separate the constants. And we're going to separate the sum. Right? So I'm going to do the sum of each term and kind of get the I by itself. Because if we're summing I, everything else is a constant. So we're going to get the limit as n goes to infinity. The first constant, okay, I cubed stays after the summation. 16 over n to the 4th is considered a constant. Right, because it doesn't have an I in it. Plus, here the I is going to stay after the summation. 20 over n squared is considered a constant. All right, so there, after I separate those constants out, this is what I got. All right, so now I can substitute what the known sums are for I cubed and I. So I'm looking for the limit as n goes to infinity, 16 over n to the 4th. All right, the summation of I cubed is n times n plus 1 over 2 quantity squared. All right, be careful here, but when you cancel, and then we're going to get 20 over n squared. The summation of I is n times n plus 1 over 2. All right. So I do like to cancel these, okay, and simplify them. But do remember to square the 2. All right. So we have n squared, n plus 1 squared, 2 squared, which is 4. So if I cancel this, 16 reduced by 4 is 4. Okay, and this is now a 1. Right? And then if I cancel here, I can cancel an n, but remember we have an n squared here. So I'm going to cancel the n squared with the n to the 4th, so I have n squared on the bottom. Right? Now, over on my next fraction, I can let the 2 and the 20 reduce. I can let the n cancel. You just have to be really careful when you've got an I cubed in there. All right? So now we got the limit as n goes to infinity. Up top, we have 4 times n plus 1 squared over n squared. Right? Here we have 10 times n plus 1 over n. Everybody agree? All right. What's the highest power of the first fraction? We got an n squared over an n squared, right? No. If they're the same power, guys, the n squareds are going to cancel out and you're left with 4 over 1, right? Same thing here. The power of n is the same. We have n to the first power here and n to the first power here. So if we divide everything by n, the only thing we're going to be left with is 10 over 1. So we're going to be left with 4 from the first fraction and 10 from the second fraction, which is 14. Right? And this should happen. Okay, these powers should match up. So it's not really necessary to do, to multiply everything out and divide everything by n squared. If you need to see it, please go, there's a lesson in that too. But if the highest power up top is 4n squared plus blah, 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 and the highest power down below is n squared, and you start dividing everything by n squared, right, the only thing that's going to be left with is the 4, right? And this one is 10n plus 10 over n. So if you start dividing everything by n, right, the only thing that you're going to be left with is the 10, right? So do kind of try and use those shortcuts when possible. All right, so we get a final answer of 14 here. All right, so that completes Appendix F. Right, so, and Appendix F is due Thursday night, and you have a quiz on Friday. All right, don't forget we have an exam on Wednesday as well. I'll be sending out an email announcement notification for you. All right, have a good night.